Hello everyone and welcome to lesson 6.5 on solving radical equations. I want to start with this video with just a quick question for you. It's the warm-up we did in class, and that is, if you said, let's say I had 2/5 x equal to 20, right? And I said you need to solve for x in one step, meaning you got to do an operation to both sides, just one thing, to just solve for x to get x equals, right? If you want to think, if you know the answer, you already know it. But if you're not sure right away, go ahead and just pause the video for a second, think about it. Let me talk about it, yeah? So, yes, you could times by 5 and then divide by 2, right? But I'm giving the sort of expectation you have to do this in one step, operate with one thing. And the way you would do this is, if you want to, we're going to call it canceling, right? You want to cancel a fraction with multiplication. You multiply by the reciprocal, yeah? So I say multiply by reciprocal. The word there, reciprocal, yeah? What that is if 2/5 is your fraction, then the reciprocal of 2/5 is 5/2. It's just flipping the fraction over, yeah? So what I'm going to do is I'm going to multiply both sides by the reciprocal of 2/5, which is 5/2. And I'm going to get rid of this stuff. So, of course, if I do it to the left side, I'll do it to the right side as well, multiplying both sides by 5/2. And watch what happens. What is 5 times 2? Well, that's 10. And what's 2 times 5? Well, that's 10. And now this fraction is 10 over 10, which is 1. So this is what I meant by canceling, because now you just get 1x, right? And then on this side, all you have to do is multiply 20 times 5/2. You might say, a fraction. I say, look, it's not that bad. 20 times 5 is 100. And now put that over 2. Dividing by 2, you get 50, yeah? And that's my answer to this problem. Now, if you understand that, then what we're going to do is extend this to rules of exponents, yeah? So let me erase all this. All right. So let's say I had a different kind of, let's say x to the 3/2, like so, yeah? Not even, you know what? X plus 1, yeah. X plus 1 to the 3/2 equals, I got to pick a nice number here. I'm going to pick 8, yeah? Okay. So the question is, how do you solve this, right? Well, you need to get rid of that exponent of 3/2, because obviously, our goal is to isolate x, say x equals, but you got to do something to this power to get rid of it. And we just saw in that previous example that, if you did 3/2 times 2/3, that would equal 6 over 6, which would just get you 1. And then that would just be x plus 1 to the 1, so you'd sort of get rid of the power in that way, right? But you can't just multiply the exponent like that. You can't just say, multiply both sides by 2/3, because it's an exponent. But there's a rule we learned, and that rule is, if you have something to a power, an exponential term like this, and then you exponentiate it, you raise it to another power, the rule is that you can multiply those, right? So if your goal is to multiply the exponents, then you can achieve that goal by raising that expression to that power, yeah? To demonstrate, what you would do is you would say, here's x plus 1 to the 3/2. I'm going to take that, I'm going to group it with little brackets here, and I'm going to raise that to the power of 2/3, yeah? And of course, if I do that on the left side, then I will also raise 8 to the 2/3, like so, okay? And what happens here is the exponents, right? I'll just put this on the side here. You do 3/2 times 2/3, you just get x plus 1 to the 1, and then you don't really need those parentheses anymore, right? Because the left side just becomes x plus 1 equals, and now you have this, rational exponent expression, 8 to the 2/3, you say, well, we covered that in 6.4. And if you need a quick reminder of that, maybe go check that video out real quick. But 8 to the 2/3, this is something I'm hoping you're working towards knowing and evaluating this mentally. But the math that's written out would say that 8 to the 2/3 is the same as saying the cube root of 8 quantity squared. Yeah? Again, that's in lesson 6.4. Okay, so if you want to go check that out, you're not sure, what the heck? 8 to the 2/3, huh? Go check out that video because you need to be able to do that, okay? But, excuse me, I'm coughing. I'm so excited. 8 to the 2/3 is the cube root of 8 squared. And of course, the cube root of 8 is 2, and then you square it, you get 4. Oh my gosh. So the right side becomes 4. And then, of course, x plus 1 equals 4, so minus 1 for both sides, and you get x equals 3. And we're happy, right? Because we did it. And this is basically it. In fact, if you feel confident, you could probably stop watching the video right now. But there's actually a few things I need to talk about in other examples because there's a few specifics to this. But if you understand this idea that you just raise to the flip of the fraction as a power, that's it. That's the premise of the lesson, okay? But there are a few things you're going to have to look out for when we do this, okay? Okay, I'll leave that there. So let's go to my official typed up notes. And what I'm going to do in this video, and feel free to skip around as much as you need, is I'm going to show you sort of two methods of tackling these problems. They're both essentially the same. Algebraically, you're actually doing the same thing, but it appears different in the way you write it, okay? And so I want to just demonstrate both methods side by side. You can kind of get a comparison between the two, and whichever one you like more, you can use and stick with that method. Or maybe you like to flip-flop in between and use both, okay? So the two methods of solving are using inverse operations and then this thing I just basically taught you, which was raising to the reciprocal power. So I've got a basic example, number 1 here, that I want to sort of show side by side how this goes, right? You do inverse operations. So what does that mean? It means the same way in lesson 6.2, when you found the inverse function, right? Remember when you would swap x and y and then solve for y? Remember that from lesson, finding inverse functions? It's basically just that. It's using the opposite operation, the inverse operation, I should say, to undo everything until you've got x isolated. So you probably already kind of know what to do here. If you're looking at this example, we need to get x alone, and the first thing we're going to do is add 17. Let's just switch to red here. So what this becomes is say square root of x plus 3 cubed, and it adds 17 to both sides, which, goes away here, and 10 plus 17 is 27. Now, the goal is to find x. So you just keep thinking, what is the outermost thing, and then what inverse operation do you do to get rid of it? Well, right now, the outermost sort of symbol is that square root symbol. And of course, we've talked about in the past, if you want to get rid of a square root, the inverse operation of square root is to square, yeah, to raise to the power of 2. So I'm going to take this, and I'm going to square both sides. And what that does is it gets rid of the square root, and you've got x plus 3 cubed equals 27 squared. Now, pause. This is 27 squared. Here's the thing. On the quiz and on the test, you're not going to get a calculator. I'm sorry. I'm not giving you one on this one because you don't really need it, yeah? And I want you to be able to build your algebra skills in such a way that not that you have to do heavy arithmetic, but that you find ways to avoid it. You say, what? I'm saying, look, this says 27 squared, which means 27 times 27. And you could stack that and then do hand multiplication or whatever. But I'm going to tell you, don't. Yeah? Don't do that. Just leave it as 27 squared, and we're going to see something happen. Yeah? So let's zoom in here. Notice how that says x plus 3 cubed. So naturally, the inverse operation of cubing is to take the cube root. So I'll take cube root of both sides like so. What this does is it eliminates the power of 3, and I say it's x plus 3 to the power of 1, but I don't need to write that. Now, the right side is now the cube root of 27 squared. But I'm going to do a little aside here. In the last video, 6.4, we talked about this rule. The nth root of a to the m is equivalent to the nth root of a to the m. Yeah? You can put the power m on a directly, or you can put it sort of after the root. And the reason that's useful here is you can say, well, let me take the cube root of 27 and then square that. Now wait a minute. What's the cube root of 27? 27 is a perfect cube. It's 3 times 3 times 3. So the cube root of 27 gets me 3, and then you still have that exponent of 2. And of course, 3 squared, 3 times 3, is 9. So what I have here is x plus 3 equals 9. Subtract 3 from both sides, and we have our answer, x equals 6. Yeah? And that is that. And that's inverse operations. And you know that. Yeah? I think with the math you've done in Algebra 2, you're familiar with this. And that's just a good review for you. Okay? Now, the other method, which is reciprocal powers. Yeah? So I'm going to take it right from this first line here. Remember that I added 17, right? I added 17. So I'm going to go ahead and do that. So I got square root of x plus 3 cubed. Excuse me. And this equals 27, right? Okay, well, if I look at the square root of x plus 3 cubed, I'm going to rewrite that using a rational exponent, yeah? Meaning the power is 3, but the root is a square root, which means the index is 2. That means it's equivalent to x plus 3 to the power of 3 over 2. And then you can say that equals 27. And now, with that example I started the video with, right? If you want to get rid of the power 3 halves, you got to multiply it by 2/3. But of course, you multiply powers by raising to a power. Sorry if my voice is kind of cracking or anything. So I'm going to raise both sides to the 2/3, because 3 halves times 2/3 is 1. And that just gets me x plus 3 to the 1. And now you've got 27 to the 2/3, which, if you did enough of 6.4 practice, you know is the cube root of 27 squared, which is 9, right? Cube root of 27 is 3. 3 squared is 9. We already covered that. Subtract 3, and I have my answer yet again, right? So I put these side by side. You are actually doing the same thing, because here you're kind of doing it step by step. You're squaring it to get rid of the square root. You're cube rooting it to get rid of the cube. Well, in here, you're doing both at the same time. That power of 2/3 is simultaneously squaring, but also taking the cube root, which is what you did in those 2 steps right there. From there, all the math is the same. So it's really just preference. Do you like it written in this form, or do you like this fraction exponent idea? Yeah? And I leave that to you. But don't stop the video now, because there's something we need to talk about. And that's going to come up in example 2. All right? Notice it says careful. We got to be careful with doing this, okay? So I've got my equation right here. You can see it. 5 times blah, 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 blah. And general practice is always to isolate the term you're looking for, right? So like you want to get that thing alone before you do anything. So divide both sides by 5 to begin with, okay? And that just means, okay, so you're going to have 3x plus 2 to the 2/3 equals 20 over 5, which is 4. Now, before doing the inverse operation way, I'm already in rational exponent form, so I'm just going to do that, right? I'm just going to say this is 3x plus 2 to the, what was it? 2/3 equals 4. But what we just talked about, I'm going to lasso this, pull it down a little bit. What we just talked about is how do you get rid of this power? you raise both sides to the reciprocal power. So the reciprocal of 2/3 is 3/2. So you say, okay, I put this to the 3/2. I put 4 to the 3/2. And so this just becomes 3x plus 2 equals 4 to the 3/2 means to take the square root of 4 and then to cube it. Square root of 4 is 2, and 2 cubed is 8. So I get 8 here. Now I just solve for x, la-di-da, minus 2 from both sides. I get 6, divide by 3. I get 2. Hooray! Yay, yippee, woo, right? And we did it. And so you're like, oh, well, okay, great, Mr. Spake, but why does it say careful, right? It doesn't seem like we did anything wrong. And I would say, yeah, I agree. I think everything, based off everything I just said, that's how that works, right? I said, well, hold on. Go back to the other method, inverse operations, right? To write this as 2/3 means, I'm going to erase the 2/3, means it's the cube root of that thing squared. So it's a power of 2, but it's underneath a cube root, yeah? So let's do our inverse operations to isolate x. Obviously, the cube root comes first, so we're going to cube both sides to get to, undo that cubic. And you get 3x plus 2 squared equals 4 times 4 times 4. That's 64, yeah? And now you have an exponent of 2, so to get rid of an exponent of 2, you take a square root of both sides. And you get 3x plus 2 equals 8. And at this point, if we were in a live classroom, I would stop and I would say, students, I've made a mistake. I'm forgetting something. What is it? Yeah. Of course, you could think about it for a second. If you want to pause the video, think, scratch your head, right? You say, You say, right? You say, this is a scratching motion. Yeah. So what is he forgetting? Well, in Unit 4, we talked about that when you take a square root, you got to put a plus or minus next to it, plus or minus. The reason is, what we're saying right here is something squared is 64. And the thing is, well, 8 squared is 8 times 8 is 64, but negative 8 squared is also 64 because a negative times a negative is a positive. So you have to put plus or minus here. Otherwise, you're forgetting one of the possible answers, right? And that is the thing that we didn't catch in the reciprocal power method, right? Because when you raise to the power of 3/2, what are you doing, right? You're saying 4 to the 3/2. That means you're taking the square root of 4 and then cubing it, right? That means since you're taking the square root of 4, you got to do plus or minus, yeah? But you could just leave that on the outside. So my actual answer says plus or minus 8. Now, this work already solves for positive 8, but you have to solve it again. 3x plus 2 equals negative 8 now, and then isolate x. So 3x equals negative 10, therefore x equals negative 10/3. And I have now my 2 answers. So the takeaway from this is, we love the reciprocal powers method, right? Ooh, we love that. It's nice, it's easy. You just flip the fraction, raise it to both sides, and it's gone, right? But something to be careful with that is if the denominator is 2, or more generally, when you raise both sides to a power with an even denominator, so it's a square root, a fourth root, a sixth root, right? Then you need to remember to write plus or minus on your result. Because when you raise something to an even power, negative answers could exist, right? Negatives could be raised to an even power to get that positive number. And so we have that, okay? So that's the main takeaway. Now, with both examples 1 and 2, I've kind of neglected to do something, and that is checking for extraneous solutions, yeah? If you go back to Unit 2 with absolute value functions, right? Absolute value x, we had to check our solutions there because absolute value is very particular. It's a piecewise function split into two pieces over two different domains, subdomains, right? Well, square root x, well, it's not quite split into two pieces, but it has a very limited domain and range, right? It's 0 to infinity for both the domain and the range, which means you can't put in negatives and it won't output negatives, right? So you if you have square roots involved, you should probably take your answer, plug it back in to see if it works, if it makes sense. And so what you could do, I'm not going to do it with this example because I think I can leave that to you. But if you take x equals 2 and you take x equals negative 10/3, plug them both in for x and do the evaluation, you should get 20, right? You should get 20 there. I'll let you know that they do both work and there's no extraneous solutions here. In fact, you only really need to do this if there's a square root involved somewhere, because it's the square root x one that's really finicky. The cube root x one, well, that's defined for all real numbers, right? So it's not as particular in that sense. But if you just want to be safe, right? You're like, which one is which, Mr. Spake? Just always do it, yeah? It's a way to kind of, it also lets you know, if you got an answer and you plug it back in and it didn't work, well, then that wasn't the answer, right? It's not a bad idea to check to see if your answer works, yeah? But just know, when you're dealing with square roots, it's possible to get a false answer. And example 3 down here will actually show that. So I'm going to demonstrate that here, okay? This also brings back some of the other skills you've done in previous lessons, okay? So it says solve the square root of 51 minus 5x equals x minus 11. So what we're going to do is you've got a square root here. You need to square roots to make them go away, right? So what I'm going to do is I'm going to raise both sides to the power of 2, like this and like this. Now notice how I'm saying x minus 11 in parentheses is getting squared, right? In class, I give you guys maybe 2-3 minutes to try this for your own. And there's always, I'd say 20 to 30% of the class makes this mistake. And I'm just pointing it out. It's not a big deal. I don't judge anyone for making a mistake. I sometimes make this mistake still after all my years of doing math. X minus 11 squared. Sometimes people say that that's x squared plus negative 11 squared. So it's x squared plus 121. Right? This is a classic algebra mistake in 1 and 2. That's not how exponents work with binomials, right? X minus 11 squared, just as a good review, is x minus 11 times x minus 11, right? And, okay, the left side becomes this. But the right side, you're going to have to use distribution. So, if you like the acronym FOIL or you like drawing the box, whatever, right? You need to distribute the stuff on the right side. So x times x is x squared, then negative 11x, then another negative 11x, and then a positive 121. Yeah? And so I'll kind of combine my like terms there in the middle, saying that's negative 22x, right? Okay, now you might be asking, well, what now, Mr. Spake? And I say, you know exactly what now, because in Unit 4 on quadratic functions, I could have given you this problem to solve, and you'd been able to do it. You say, huh? What? And I say, look, it's a quadratic equation, right? You have a linear term here. You have a quadratic here. How do you solve quadratics? Answer, factor, right? At least that's what you should try first. You could do quadratic formula, but nah. We're going to always try factoring first because it's usually faster, unless you disagree with that, of course. So I'm going to minus 51 from both sides here and add 5x to both sides here. You're fine to use quadratic formula. I don't have anything against it, okay? It's just, I don't know. It's good to factor. I don't know. I like factoring. It's great. And I got this, right? I just moved everything to one side there, and I have my quadratic trinomial. So I factor. You can set up a little puzzle. What two numbers multiply get 70, add to get negative 17? Pause, think about it if you'd like. The answer is negative 10 and negative 7. And then you'd say, oh, okay, so because this is a 1, I can sort of shortcut it and say this factors as x minus 7 times x minus 10. Yeah? And what that means is the solutions, or roots, if you recall that word, the roots of that polynomial are x equals 7 and positive 10. And so we're done, right? Except, no, hold on. I told you the whole point of this example, yes, 1 is to show you that quadratics come back, but 2, to show you that extraneous solutions can happen. So we're going to take 7 and plug it back in. So it says the square root of 51 minus 5x equals x minus 11. And if you plug in 7 on the left side, you get 51 minus 5 times 7. That's square root 51 minus 35. And if you got to do that, the difference between those looks like 16, right? And the square root of 16 is 4. Now, let's say you do the right side. You put in 7 minus 11. Well, 7 minus 11 is negative 4. So conclusion, does negative 4 equal 4? No, it doesn't, right? That means that 7 is not an answer, okay? And we can repeat this with 10, okay? So actually I can just change a little bit of the math here. That becomes a 10. This will become a 10 as well, okay? So 51 minus 5 times 10, that's 51 minus 50, which is just 1, right? And so I say, okay, that's the square root of 1, which is 1. But 10 minus 11 is negative 1. That means 1 does not equal negative 1. Oh, shoot. That means 10 doesn't work either. Therefore, there are no solutions, yeah? Or if you want to be really fancy like Mr. Spake and how he likes to write it, x belongs to the empty set, yeah? That's to say that x is a set of no answers, yeah? It's nothing. Nothing answers this problem because it's not true, yeah? This is never going to be equal. It's just not, no matter what number you plug into it. You can graph it too. Well, let me just take a moment to do that. Just to show you, right? Oh, there's my leftover pre-cal video that I was doing for my on-ramps kids. 51 minus 5x, and then x minus 11, like that. Notice, right, that the square root curve and this linear line, they never touch. They get pretty close, but they actually never intersect, so there's no solution, okay? So something to keep in mind, right? Check for extraneous solutions, especially if you have a square root, okay? Because square roots, if you take the square root of a negative, it's imaginary. We're interested in real solutions right now. But the other thing is the range of square roots is all real or is not all real numbers. It's 0 and up, right? It's 0 to infinity. So the thing is you didn't really have to do all that math in the square root there, actually, because look, what this says is square root of something equals 10 minus 11, which is negative 1. Well, the square root of whatever, it's never going to be negative, kind of like absolute value, right? Remember how we said absolute value is never negative because it never outputs a negative value? Well, same thing here. Square root never outputs a negative value on its own like that. So make sure you check for extraneous and you do that, okay? Okay. There's another few examples here. If you're watching this, learning it from home for the first time, I would pause and try all 3 of these on your own without me. I think I'll quickly put up the solution real quick. But I'm not going to spend too much time talking about 1 and 2. I am going to spend a little bit more time talking about number 3. So for number 1, again, you could pause and try this, but the solution is minus 9 from both sides. Our goal is to isolate this expression. And maybe what's tricky for students in this problem is that negative, right? What do I do with the negative, Mr. Spake? Well, you have a negative on both sides, so divide by a -1, and they become positive. Yeah. And then the power, I forgot my x. The power is 3/4, so you're going to raise this to the power of 4/3 on both sides. Yeah. 3/4, 4/3 cancels. You get 5/3 x minus 4 equals 8 to the 4/3. Now, 8 to the 4/3 means to take the cube root of 8 and then to raise it to the 4th. Cube root of 8 is 2, and then 2 times 2 times 2 times 2 is 16. And before I finish off this problem, you might ask, do I need plus or minus here? I say, well, no, remember the rule was only an even denominator. That's actually why we didn't do it at example 1 here, the basic example, because when you raised it to both sides, you did 2/3. The 3 was an odd denominator, so you didn't need to do that, okay? Cube roots, they're defined for all real numbers, so there it is. Okay, so finishing off this problem, you got 5/3 x equals 20 by adding 4 to both sides. Of course, you'd multiply by 3, or you could do the reciprocal, right? But I'm just saying multiply by 3, you get 60, divide by 5, 60 over 5 is 12, and that's my answer, yeah? And you should do, on your own time, take that 12, plug it back in. I'll let you know that it works. Yeah, it works. So if you don't want to do it, you don't have to, okay? I'll do number 2 now. Let's get that one done. Notice that the square root is not isolated, right? He's actually in addition to the 3x. So we would like to isolate that by subtracting 3x from both sides. Because, if you square something that's added with something, it actually doesn't get rid of the square root. And that's what we're going to see on the next problem. So minus 3x from 5x, you get 2x. But now that the square root's isolated, you could square both sides like this, put parentheses around it and square it. This drops the root symbol on the left side, but be careful here. 2x squared means 2x times 2x. That's 4x squared, yeah? I see just a few students make that mistake of saying it's 2x squared. Just watch out, something to be careful about, And then this is a quadratic again. Yay! Oh my gosh, I love quadratics. Yes. So how do I solve quadratics? I set everything equal to 0 and I factor, if possible, right? If possible. What that means is 4x squared plus 18x minus 10 equals 0. And of course, if I can't factor, you'll have to use quadratic formula. And you can thank me for giving maybe 1 or 2 of those on the homework. You're welcome. Where you can't factor, you have to use formula. Okay. Anyway, factoring time. 4 times -10 is -40, right? We're doing that, and then 18 down here. This will be 20 and -2 to make this work. In which case, we're going to do the grouping method. 4x squared plus 20x minus 2x minus 10 equals 0. And then you just group. So we're going to GCF the first group, the first 2 terms. You get 4x factors out to get x plus 5. Then we're going to factor out a -2 to get another x plus 5 here, leaving us with 4x minus 2 and x plus 5, which equals 0. And therefore the roots, right, you set this equal to 0. You set this equal to 0. My 2 solutions I'm going to get here is... maybe I should write that out for you just in case, huh? 4x equals 2, so divide by 4. You get 2/4 here, right? So you got x equals 2/4, which is a half. And if you minus 5 from both sides, x is -5. But what should you do with these answers? Check them, right? Go all the way back up here to the original, check them. You could actually check them on this line before you start squaring stuff. So what I had was the square root of 10 minus 18x equals 2x, right? Because that's fine. That's whatever. Plug in a half, right? I'm going to do it in blue now. 10 minus 18 times a half Does this equal 2 times a half? Well, half of 18 is 9. 10 minus 9 is 1. Square root of 1 is 1. And of course, 2 times a half is 1. So 1/2 works. Hooray! We did the same thing, but now with -5, right? So I'm going to erase the half, put a -5 in there, -5 in here, and notice 10 minus 18 times -5. Well, -18 times -5 is 90, positive 90, which gets you square root of 100, which gets you positive 10. But 2 times -5 is -10, and those are not equal. Therefore, -5 is not a solution. Okay? The only answer to this problem is 1/2. Okay? -5 was what we call extraneous. All right. Okay, one more example of solving, and then I get to talk about natural domain. So, number 3. It says solve this problem right here. Now, this is just notable because it has 2 square roots, right? Separated, 2, not multiplied. They're separated. So the question is, how do you deal with this? I do recommend that you try this on your own before I go through it, but I'll show you now, okay? So when you have this, you got to get rid of both square roots, but you're going to get rid of them one at a time, all right? And this is going to happen, I don't know frequently, but it's definitely going to happen in pre-cal. It's definitely going to happen in calculus where you're not just done after one move, you know? Let me show you to show what I mean, yeah? You're going to square both sides, and that's going to get rid of the square root on the left side to become x plus 9. But on the right side, well, root x plus 1 is grouped together, and that's a binomial. That means you have to do square root x plus 1 times square root x plus 1. You don't just get to cancel the square root, if that makes sense. You don't just say, oh, it's root x squared and plus 1 squared, right? Because that would be the same mistake as mentioned earlier with the other binomial, right? Earlier in the video. Now I'm going to multiply this out. Root x times root x. If you don't know what that is, that's square root of x squared, which is x. Technically absolute value x, right? But whatever. We're going to say that that comes out to x. And then x times 1, that's root x. And then another 1 times root x, that's another root x. And then a 1 times 1 is a 1 right here. Now notice on both sides, I've got x's. So I'm going to say doop, doop. Get rid of those. And I'm also going to minus 1 from the 9, just because. So this gets me 8 equals. And then the 2 root x's here, I mean, that's literally 2 root x. Okay, there's 2 of them. So it's 2 times square root x. You could get rid of that 2 pretty easily through division. Say that 4 equals the square root of x. And now you just say, oh, well, you have a square root, so square it. Square it. And you get 16 equals x. Yeah? And that is our answer. You can check for extraneous, but I know this video is already getting a little long. It does work, okay? We're going to put a little happy face. It does work. If you want to say, yeah. Okay. It works. You can plug 16 in, and it's true, okay? What was interesting about this problem is when you squared away the square root, you still had one to deal with. And if you thought, uh-oh, I did that wrong, no, you didn't. You just have another square root still to deal with, and so you just do the same thing. Isolate the square root and then square it away again, yeah? And that's how you approach problems like that. And always remember, check for extraneous, especially if we get square roots, yeah? Okay, so that does it for solving, which is the majority of what this lesson is over. There's one last little tidbit here, though, and that's on what we call natural domain. And if I'm not careful, I'll talk about this a little too long. So I'll try to be concise for you, okay? In higher math classes, you're going to have deeper conversations about what a domain is and what a range is and what that means to, like, what does it mean to input a number into a function? What's allowed as an input, right? Now, when we say natural domain, there this is just the domain you've been talking about your whole high school life. Yeah, I could have just called this domain. Okay, there's really not. It's not super necessary to write the word natural here, but the reason I put this word natural here is kind of on a technicality. Okay, because look, in Unit 4, we talked about the square root of -4, right? And we said that, oh, that doesn't, you could say it doesn't exist, but it exists. It's something we call 2i. We call it an imaginary number, a complex number, right? So it's in another field of numbers. By the way, that's the word, field. That's sort of higher above the real numbers, right? Is complex numbers. It includes everything, right? But in this unit, and in general, for most of algebra, pre-cal, and calculus, you don't really need complex answers unless that's the context you're working in, yeah? So sometimes we're going to be saying, yeah, I want 2i as an answer, and I'm going to say that's the answer. But sometimes I'm really just interested in real outputs, yeah? Real outputs. And if the answer isn't real, then I don't need it, yeah? Other contexts, an imaginary answer will matter. An imaginary answer will be useful and be used to do something or accomplish something. But for the most part, in high school math, aside from just kind of learning imaginary numbers and sometimes using them in classes like pre-cal and calculus, we're mostly interested in real outputs. What a natural domain is, when I say natural domain, I'm talking about the numbers that a function naturally takes on such that when you put it in, you get a real output. Yeah? What that means is square root of -4. It exists. The output exists. It's 2i, but it's not real, right? It's imaginary. And so what I would say is that -4 is not in the domain of the square root function, right? And of course, oh yeah, well, think about your parent function. It's graphed from 0 to infinity, right? Both the domain and the range. So that domain that we've been saying, 0 to infinity, that's the natural domain of a square root function. The idea is, though, that if you were to travel into a higher math class, you could let the domain be all real numbers, right? As if you were interested in non-real outputs, okay? And so hopefully that explanation kind of makes some sense to you as to why I'm using this verbiage of natural domain, because we're interested in numbers that get us real numbers. We're not interested in inputs that get us not real outputs. Okay, so that's the justification as to why. Here's the what and how, yeah? So how do you figure out a square root function's domain or natural domain? You just set the inside more than 0, because here's why, right? Square root x, if you take the square root of a negative, this leads to an imaginary result. That means I need to take either the square root of 0 or I need to take the square root of a positive number. So whatever expression, I'm going to make a little cloud here, right? The square root of cloud, I want the thing that's inside there, the cloud, needs to be positive or 0. And you can represent that by writing an inequality, saying that cloud is greater than or equal to 0. Yeah? When I say cloud, I'm just talking about the thing inside the square root. Yeah? And I'll exemplify that with the next 3 examples. So in number 1, right, you have various transformations here, but only the input affects the domain. Only this expression inside the square root affects the domain. The negative on the outside and the 10 on the outside affect the range, but it does not affect the domain. So what do? I said, well, you take the inside of the square root function, 4 minus 3x, and you set it greater than or equal to 0. At this point, you just use your Algebra 1 and 2 skills to solve. So isolate x by subtracting 4 from both sides. I get negative 4 here. And then I'm going to divide by a negative 3 to isolate x. But keep in mind, you are dividing by a negative. And when you're working with inequalities and you divide by a negative, you flip the inequality sign. Also on the right side, negative over negative. That's a double negative, makes a positive. And we're done. That's it. And that is it, okay? That's how you find the domain of a square root function. I mentioned this now. It's not totally related with solving things, but it's kind of. You're using solving skills to do it. And when you get, especially to a class like calculus, knowing what your domain is pretty helpful, yeah? It's going to help you rule out answers. It's going to help you think about those questions deeper. And so that's why we talk about it now. It's kind of give you a tool for the future, something to think about and use in future math, okay? You could also write this interval as numbers less than 4/3 are negative infinity up to 4/3 bracket, okay? That's also how you could write that. The next two examples are the same thing, but I've just put it here in the lesson to remind you that inequalities are things we've learned before, and then you gotta, oh yeah, I gotta remember how to do those, right? So with number 2, same thing. You set the inside of the square root greater than or equal to 0, but this is a quadratic. So how do you solve quadratics, right? In particular, how do you solve quadratic inequalities? Well, you need to find the roots, and then you need to think about whether that parabola is facing up or down or whatever. You're saying, what again, huh? Let's say, well, first start by factoring it, okay? You say this negative 15, this is 2. And the two numbers that work here are 5 and negative 3. So the polynomial factors as x plus 5 and x minus 3. This is greater than or equal to 0. Now, you identify your roots here. You say, what are the roots? The roots are negative 5 and positive 3. Remember, this is something we did in Unit 4, yeah? Back in the quadratics unit. So now that you have your roots, you draw a little number line like so. And you say my roots are at negative 5 and 3. Those are my x-intercepts, right? And then I just think, okay, well, how does the parabola pass through these points? Does it look facing up, or is it facing down, right? And you know this because from Unit 4 and 5 we said that the lead coefficient tells you that, right? The lead coefficient tells you the end behavior, right? Or it's an aspect of it. So it's a positive 1x squared. That means it's opening upwards. Yeah? Opens upwards like it. So upward facing parabola. Now, I'm going to switch to a red here. We want to know when it's more than 0. That means above 0. Yeah? When is this quadratic above 0? Well, it's above 0 here, and it's above 0 here. And if you're saying, huh, what? How do you know it's 0? The number line is 0, so this is above, and this is below, right? So below, that means less than 0. This is above the line, which means more than 0. So we want to be this section and this section. And on the number line, that's shading this region and this region right here. So our domain, you can use the number line to help inform this, right? It's a good visual. You're going all the way from negative infinity, extending out to the left, coming up to negative 5 and stopping there. It is included because you can equal 0, right? You can equal 0 here, but then it skips. And the other interval is bracket 3 to infinity. And we want to join both of these intervals as part of the same solution, or, well, domain. So we union them. Put them together with the union, and I've got my solution. Okay? And that is that. But notice, when I'm saying natural domain, the only real new thing in this video is just stating that you need to take the thing inside the square root and make it more than 0. Everything else is just stuff we've learned before, and we're just kind of saying, hey, don't forget this, hey, don't forget that, right? This third example, if you got the idea, you're good. But this third example here, you got an absolute value inside the square root. Same thing. You set x, absolute value x minus 2 minus 4. You set that greater than or equal to 0. And you just say, okay, well, where does this thing equal 0, right? Well, you can solve the inequality by adding 4 to the other side and then split into two cases. So you can say the positive case, which is x minus 2 equals 4, and the negative case, which means you flip the signs inside the bars. X becomes negative x, minus 2 becomes positive 2, and this is more than 4. And now you just solve, add 2 to both sides to get 6 here. Oh, sorry, it's an inequality though. So that's greater than equal to 6. Here you subtract 2 from 4 to get 2, and then divide by a negative 1, which effectively flips the sign. You get negative 2 here. And so I have x is less than negative 2, but it's more than 6, right? And so you can put that on a number line. Here's negative 2. Here's 6, right? But you kind of remember that when you would check for extraneous in this way, you'd really want to make sure that it is, in fact, you know, if you remember and versus or, right? There's that vocabulary. Is it simultaneously more than 6 and less than negative 2, or is it, could be either, right? You could check for extraneous by plugging in a few numbers. So I'll plug in 7 right here. 7 minus 2 is 5. Absolute value 5 is more than 4. So this is good. So more than 6 is true, which means it's probably this, right? But you can check 0 is in between those. 0 minus 2 is negative 2, but absolute value is 2. Is 2 more than 4? No, it's not. Then pick negative 3, right? Negative 3 minus 2, that's negative 5. But absolute value of negative 5 is 5, and 5 is more than 4. So we're good here too. Yeah, so it's both those intervals there. Meaning our domain is negative infinity up to negative 2, bracket, union, bracket 6 to infinity. Okay? And that is that. That's all of those problems nice and worked for you. I do want to show you one last thing is graphically, what do these things look like, right? So I'm going to do the x squared plus 2x minus 15 one. So if you come over here and you say, oh, hey, Desmos, can you graph me x squared plus 2x minus 15? And you'll notice this red curve of the graph. I'll make it bold for you here. You can see how it's graphed for the x-intercepts at negative 5 and 3. That red curve extends to negative infinity from the negative 5, and it extends to positive infinity from the 3, but there's nothing in between, right? There is no graph in between, and that's because if you were to plug in something between those numbers, it would get you an imaginary output, right? Get you a square root of a negative, which isn't real, which isn't graphed on the real plane, yeah? And so that's what we mean by natural domain. It's the domain that the function naturally takes us on so that you get real outputs, basically what you would see on a graph, yeah? Okay, I think that covers everything about this lesson that you need to know. Hope you enjoyed, and there it is. Good luck, take care, and have a good day.